The development of composite materials over the last few decades has completely transformed how some of the most advanced engineering problems out there can be solved. It's allowed the development of materials with unique thermal properties that can better handle the blistering temperatures of atmospheric re-entry, for example. And has pushed the limits of jet engine design through the use of lightweight fan blades that have carefully tailored mechanical properties. But what exactly are composite materials, and what makes them so special? Let's find out. A composite is really just any material made from two or more distinct constituent materials. They can be found in nature. Wood is just one example of a natural composite material. But they can also be engineered, where different materials are carefully combined to develop all sorts of incredible and exotic composites that have mechanical, electrical, thermal, or even magnetic properties that have been tailored to suit a specific application. In most composites, one material, called the dispersed phase, is contained within another, called the matrix phase. The ability to carefully select each phase to optimize the properties of the material for a specific application is what makes composites so powerful. The dispersed phase is usually what provides the desirable material properties, like high strength or improved ductility, and is usually either a ceramic or a metal. Composites are often categorized based on the form of the dispersed material. This is a particle-reinforced composite, but they can also be fiber-reinforced, either with short or with continuous fibers. The matrix material is used to form a mechanical and chemical bond with the elements of the dispersed phase and allows loads to be transferred between them. It holds everything together, and it protects the dispersed phase from the environment. Composites are also categorized based on the type of matrix material, which can be a polymer, a ceramic, or even a metal. Probably the most widely used composite materials in engineering applications are the fiber-reinforced polymer matrix composites. This category of composites includes glass-reinforced polymers, also called GRP or fiberglass, and carbon fiber-reinforced polymers, or CFRP. These composites usually have an epoxy matrix, which is a thermosetting polymer, and the dispersed material is glass or carbon fibers, which make up around 60% of the material by volume. The most basic form of fiber reinforcement is unidirectional tape, which has all of the fibers running in the same direction. The individual fibers are grouped together into bundles, which are held together with stitching or using a chemical binder. In the case of carbon fibers, these bundles are called tows. Each tow usually contains anywhere from 3,000 to 24,000 individual fibers. A typical fiber is around 10 microns in diameter, which is 10 times thinner than a human hair. Any fiber-reinforced material that has fibers all running in the same direction will be highly anisotropic. Its material properties will be different in different directions. If you apply a load along the axis of the fibers, the material will be stronger and stiffer than if you apply it perpendicular to the axis, because the load is taken by the stronger and stiffer fibers instead of by the matrix. This can be a good thing. If you know that your material will be loaded mainly in one direction, you can orient the fibers to make it very strong in that particular direction. In pressure vessels, for example, fibers can be aligned mostly in the hoop direction, because the hoop stress is the largest stress when the vessel is pressurized. In most cases, though, you need good strength and stiffness in several directions at the same time. In the case of this pressure vessel, there will be axial stresses too. So we'll also need some reinforcement in the axial direction, either with axial or helical fibers. This is why components made from fiber-reinforced materials are built up by stacking multiple layers that have different fiber orientations. Each layer is called a lamina, or a ply, and the stack is called the laminate. In this laminate, the 0-degree layer provides strength and stiffness in the axial direction. The 90-degree layer provides it in the transverse direction, and the 45-degree layers provide it in the shear directions. If enough layers are stacked with the correct orientations, the laminate can have very similar properties in all of the in-plane directions. This is called a quasi-isotropic laminate. Fibers can also be arranged in weave patterns, which have fibers running in 2 different directions. There are hundreds of possible weave patterns. This is a plane weave, but the twill weave pattern is also commonly used. There are slight differences in how different patterns behave. A twill weave is more flexible and will conform more easily to a curved surface, for example. Weave patterns have good stiffness and strength along the 2 fiber axes, but they're weak at 45 degrees, so they should be layered in different orientations if quasi-isotropic properties are needed. Once the laminate structure has been defined, the different fiber layers need to be assembled and combined with the polymer matrix to create the final composite part. One way of doing this is the wet layup method, where fiber layers are built up in a mold, and the resin is applied to each layer using a roller or a brush. The number of plies and ply orientation are carefully selected to achieve the required properties. An alternative method involves the use of pre-preg, tapes or sheets of fibers that have been pre-impregnated in a partially cured epoxy resin, meaning they can be applied to the mold without needing any additional resin. The laminate can then be vacuum bagged to ensure it conforms well with the mold and to remove any voids, and it will then need to cure. The polymer matrix is usually a thermoset, a polymer that irreversibly hardens when heated, in which case curing is done at elevated temperatures in an oven. Filament winding is another manufacturing method where a machine is used to wind unidirectional tape that has been impregnated with resin around a mandrel. Once complete, the mandrel can either be left in place or removed, and the structure is cured. Other methods like injection molding can be used for composites reinforced with short fibers, since the orientation of the fibers can be arbitrary. So why are fiber-reinforced materials so special? To find out, let's look at their mechanical properties. This graph shows tensile strength on the vertical axis, and Young's modulus, which represents the stiffness of a material, on the horizontal axis. Let's plot a few common engineering materials: titanium alloys, aluminum alloys, mild steel, and high-strength steel. Next, we can add carbon fiber reinforced polymers. A plain weave carbon fiber material has a tensile strength of around 600 megapascals, and a Young's modulus similar to aluminum, although the exact properties will depend on a number of factors, including the type of polymer matrix that's used and the layup configuration. A unidirectional carbon fiber material is much stronger than the plain weave, and has higher stiffness as well, although remember that this is only true if the load is applied along the fiber axis. These materials correspond to standard carbon fiber grades, but there are also high strength, high modulus, and ultra high modulus variants. We can also plot glass fiber reinforced polymers, which have lower stiffness but very good tensile strength. E-glass and S-glass refer to different glass fiber compositions that are optimized for different applications. E-glass is the most commonly used type and was originally developed for electrical insulation applications, and S-glass was developed for structural applications and has improved strength. The really amazing thing about these fiber-reinforced composites only becomes apparent when considering their mass. If we plot specific strength and specific stiffness on this graph by dividing by the material density, it's clear that the composites far outperform traditional materials. The unbelievable strength-to-weight and stiffness-to-weight ratios of CFRP materials are why they're so commonly used in industries where weight reduction is critical, like aerospace, the automotive industry, and even in sports like cycling and sailing. Glass fiber reinforced composites have lower stiffness than CFRP, but excellent strength properties on a per-weight basis, and are much more cost-effective than CFRP. They're often used in wind turbine blades and in the construction of boats, where light weight, high strength, and low cost are critical parameters. The impressive strength of fiber-reinforced composites is in large part due to the small diameter of the reinforcing fibers. The strength of a fiber, like any material, is limited by the presence of defects within its microstructure, from which cracks can form and grow to failure. The larger a fiber is, the more likely it is that it will contain more defects, and that the defects will be larger. This means that if you take two fiber bundles with the same cross-sectional area, but different fiber diameters, the bundle with the smaller fibers will be stronger. Not only that, but in the bundle of smaller fibers, failure of a single fiber can occur without hugely increasing the load on the remaining fibers. And the smaller the fibers, the larger the surface area between the fibers and the matrix, which means better load transfer between the two. The result is that the strength of a fiber-reinforced material increases significantly as the fiber diameter reduces. The main thing limiting the use of ever thinner fibers is manufacturing constraints. Fiber-reinforced polymer matrix composites aren't only used for their good specific strength and specific stiffness. They have many other useful properties that provide advantages over traditional materials like steel and aluminum alloys. They have excellent internal damping properties, which can be useful for applications involving dynamic loads, and they have good corrosion resistance. The polymer matrix does a great job of protecting the reinforcing fibers from the environment. They also have interesting thermal properties. They're usually relatively poor conductors of heat, and have very low thermal expansion coefficients compared to metals, which can be useful for applications requiring good dimensional stability over a wide range of temperatures. But they also have drawbacks. The cost is one. They're significantly more expensive than using standard metals. They can also be difficult to design with because their highly anisotropic nature and complex and varied failure modes make it difficult to accurately model their behavior and to predict failure. And integration of fiber-reinforced parts into a larger assembly isn't always straightforward. Welding isn't an option, and although mechanical fasteners can be used, they tend not to perform as well as they do in metals, so fiber-reinforced polymers are usually bonded to other parts using adhesives. Another drawback is the brittleness of these materials. Let's compare stress-strain curves for a few fiber-reinforced polymers alongside steel and an aluminum alloy. Fibers tend to be made from materials like glass and carbon because they have high strength and stiffness, but they're also very brittle. This means the resulting composite material is also quite brittle. CFRP in particular will fail at very low strains compared to steel and aluminum alloys. A well-known fiber reinforcement we haven't mentioned yet is Kevlar, a type of aramid fiber. Kevlar reinforced polymers are stiffer and stronger than GRP, more ductile than CFRP, and lighter than both. This makes them ideal materials for applications where excellent impact resistance is required, like in body armor. Another issue with materials that have a polymer matrix is that above temperatures not much higher than 100 or 200 degrees Celsius, the polymer will typically start breaking down, limiting the maximum temperatures the composites can be used at to well below the level of metals. If you're working with extremely high temperatures, you'll have to turn to ceramic materials like alumina, silicon carbide, and silicon nitride, because they have very high melting points, much higher than metals and polymers. They can withstand temperatures upwards of 1000 degrees Celsius. Ceramics have other properties that make them useful at these high temperatures, including high thermal shock resistance and low thermal expansion coefficients. Plus, they have high strength and high stiffness. Carbon has similar properties to these ceramics. With a melting point above 3000 degrees, it can handle extremely high temperatures. But all of these materials are very brittle. They fracture suddenly at very low strains, which limits how useful they are. And this is where, once again, the use of composites can make a big difference. Adding silicon carbide fibers to a silicon carbide matrix, for example, results in a material with significantly increased toughness. To see how this works, let's compare two ceramic materials, with and without fiber reinforcement. Both contain an initial crack. When a load is applied, the crack in the pure ceramic propagates very quickly, resulting in failure of the material. In the composite, though, the fibers bridge any cracks that form in the matrix, which prevents them from growing, increasing the overall toughness of the material. Unlike polymer matrix composites, where the aim is to have a strong bond between the matrix and fibers, so that loads can be transferred between the two. In ceramic matrix composites, the fibers are coated to allow them to slide somewhat within the matrix, so that cracks in the matrix don't overstress the fibers. The resulting composite is extremely resistant to temperature without being too brittle. Composites with a silicon carbide matrix and silicon carbide fibers are used in high-temperature jet engine turbine blades. And carbon-carbon composites have applications in spacecraft heat shields to protect from the extremely high temperatures during atmospheric re-entry. They're also used in the braking systems of some aircraft, and even in high-performance cars. Composites with a metal matrix are usually used to try and improve the strength or stiffness of a metal, which often involves incorporating carbon fibers into an aluminum or titanium matrix. But sometimes the goal is to modify other properties of the metal. One example of this is the use of magnesium in biomedical engineering. Magnesium is a very promising metal for use in implants designed to heal bone fractures, because it's lightweight and has excellent biocompatibility. Another advantage it has over commonly used metals like titanium is that it biodegrades in the body, so a second surgery isn't needed to remove the implant once the injury has healed. But it has quite low strength and biodegrades too quickly to be all that useful. Researchers have found that by replacing pure magnesium with a composite that has a magnesium matrix and a dispersed phase of ceramic particles, the degradation rate can be controlled and the material strength and other properties are greatly improved. It's really quite incredible. Particle reinforced materials can be developed for all sorts of different applications. Designing an electronic component that dissipates a lot of power, a heat spreader made from a composite with a copper matrix and diamond particles will have higher thermal conductivity than standard materials, allowing you to dissipate the heat more effectively. The composite also allows the thermal expansion coefficient of the heat spreader to be tailored to match the properties of the chip die, which helps avoid high shear stresses between the two. Concrete is an example of a much more common particle reinforced material. The matrix phase is cement, and the dispersed phase is aggregate, a mixture of sand and crushed stone. The cement binds everything together, and the aggregate improves strength, and has the added advantage of being less costly than the cement. A more recent development is the use of engineering cementitious composites. These composites incorporate short, randomly oriented polymer fibers into a concrete matrix to obtain a material that has the properties of concrete, but is also ductile, which is why it's sometimes called bendable concrete. This just illustrates that the possibilities for innovation using advanced composites really are endless. There are so many different ways materials can be combined to obtain something useful. A final category of composites is sandwich composites, where a lightweight core material is sandwiched between thin skin layers made of a stronger and stiffer material. The lightweight core is typically a foam or honeycomb structure, and the skin layers are either metals, like aluminum, or a composite, like CFRP. The layers are bonded together using an adhesive, and the result is a lightweight structure that has high bending stiffness. Under loading, the sandwich composite behaves in a similar way to an I-beam. The outer layers carry bending loads, like the flanges of an I-beam, one side being in tension and the other in compression. The core is like the web. It carries shear loads, but also increases the distance between the outer layers, increasing the second moment of area of the cross-section. Inserts are incorporated into the panel to allow the use of threaded fasteners. Honeycomb panels are used extensively in satellites as structural panels, to which instruments and communication equipment can be attached. There's no doubt that the study of composites is an exciting and constantly evolving field in materials science that opens up new opportunities for innovation. Whether for fun or for professional projects, having an understanding of the different composite types will help you design and build stronger, lighter, and better performing products. Equally important in the design process is having access to the right tools to bring your projects to life. And that's why I'd like to tell you about this video's sponsor, Onshape. Onshape is a really impressive and unique cloud-based CAD platform that has all of the functionality you would expect from modern CAD software, but also much more. And it all runs in your web browser. It has a rich parametric modeling toolset that makes modeling parts and managing assemblies easy, with loads of tools to make your workflow really efficient, like standard part libraries and the frame and sheet metal features. You can even develop your own custom features or download ones that have been created by the community. One of Onshape's most powerful and unique features is its amazing collaboration system that allows multiple people to work on the same files at the same time. Really useful if you're working with others and building something as a team. It also has a great version control system that lets you easily log changes and roll back to previous versions if needed. And because it's cloud-based, you don't need a powerful machine to run it, since all of the processor-heavy tasks are done in the cloud. You can access your files from any machine just by logging in, and they even have Android and iOS apps. You can get started creating designs of your own using Onshape for free in just a few minutes. Just head over to onshape.pro/efficientengineer to create your free account and start designing. It's genuinely a great CAD platform, and I highly recommend you check it out. And that's it for this look at composite materials. Thanks for watching.